Hello everyone. Just wait for everyone to join and then we'll start.
Hello.
Hi Rohi, how are you?
Yeah, I'm good. How are you?
Yeah, I'm doing good as well, thank you. Most probably, let's give it a start and let's continue from where we left off for the last time. But give me 1 minute. Just give me 1 minute. Oh, come. Yeah. Okay. Okay. Fine. Yeah. I think yes, we are set now. Good. So until the last session, what uh, we did a quick model or a set of predictions on the training data itself, and then we found out what was the confusion matrix. We quickly revised what is the confusion matrix, and then we were able to find out what is the accuracy of the model. Approximately out of the box, we have not really done much. We have just done the scaling of the features, and we have done wherever possible one hot encoding and dummy label encoding, post which we have got this output. Right, so we have got 80% output. Let's see if there are any other measures or any other methods in which we can improve it. So one of the possible things that we may want to do is that we have already done RFE. Why not give it a try with VIF? Right, if we can see if we can do VIF, then let's see what VIF is going to give us. If really possible, we are going to get rid of a few variables again, and then let's see if that is really going to work. So to do VIF, what we are going to do from stats models dot stats dot outlier sorry influence outliers outliers influence. That is why tab was not working. Import variance in inflation factor. Right, I believe this should work. Yeah, it did. So now again, similar to what we've done earlier, we will be creating a data frame called VIF. So I'm going to name it as VIF. PD dot VIF is equal to PD dot data frame, right? In this data frame, what we are going to do, we are going to store the column name and the VIF value, right? So how do we do that? We need the columns. We need the feature columns. So I can say VIF inside bracket. I can call this, let's say, features. Okay, and I can call this is equal to x x train, right? And I can say dot columns. This should do, right? Or I do have the columns in one data frame, right? I already took all the columns. Not sure where it went. Yeah, I think this was the one. Call to, yeah, yes, this was the one. This was called to. Why not? Why don't I take this? I can do something like this also, call to, right? I can do something like this, or I can pass all the columns also. That is not an issue. Then what I can do again, I'm going to calculate the VIF. So I'm going to add a new column in here called VIF, and here I'm going to use a lambda function. And what I would like to do is to calculate the variance inflation factor for something, right? I'm going to pass the values for I in range of all my columns. So what I'm going to do is uh, x train underscore 2 dot shape 1. So this is the length of the columns, right? So for I in range, the length of the columns, what I need is basically the variance inflation factor of the values of that column. So I'm going to pass x train colon underscore 2 dot values comma I. I'm going to pass the iterator, right? So that's I believe is going to work, right? So if I have done this properly, let me just also round the figure. So VIF's column VIF should be um, what can I do? Round of 2. So I can do a round function using VIF and pass the column name as VIF comma 2. This should round it to two places of decimal. Once I have done this, then what I can do? I can do VIF is equal to VIF dot sort. I can use sort. I hope you are able to see my screen, right, Rohit? Because I just saw a flash which says some problem with my
Yeah,
internet
yeah, I
connection.
can see. I can see.
Okay. Okay, so I'm going to sort my values by VIF, and what I'm going to do, I'm going to say ascending is equal to false. Right, I'm going to say ascend. Oh, sorry, I shouldn't have put it into single quotes because that's a boolean value. So now I should have my data frame for VIF. So I could clearly see there is a problem here. VIF of total charges and monthly charges is really very high. So this is quite high. So I can try and get rid of that. But if I get rid of monthly charges and total charges, uh, that may well be a problem because um, because oh no, 1 minute. Let me just cross check the list of columns that I have taken. So from here, I remember we dropped one column, and the reason why we dropped one column is because we have, I think, dropped it already. RFE support. We took the RFE support and then the columns. So why not? Hold on. I think we are not taking all the columns. So what happens if I take all? Oh, hold on. No. PD data frame. And yes, now let's see. Oh, yes, of course. To change everything to call now. I'm just trying to take all the columns because I just remembered we dropped one column. I don't want to create any confusions. Let me just see if this one, yes. Now I think I have almost all the columns. I thought there is one or more column which are missing. So maybe now I've taken care of everything. But now the question there is, what if I drop monthly charges? Is that going to be a very good decision? Because monthly charges may well be one of the factors where uh, people might churn. Will be a possibility. What about the total charges? Total charges is, let's say, if I have understood the business context, total charges will be like the charges the customer is paying both for the phone services as well as internet services as well as any other value-added services which they might be using. So that also has a very big impact. Let's see if we can do something with monthly charges. Let's get rid of that. Let's see if the VIF is going to increase. Right? If that VIF is going to increase, then we will see. Right? We'll see if that is really going to do anything. Mm, okay, fine. So what we can do is that I'm going to use all underscore 3 is going to call dot drop, and I'm going to use monthly charges. Although, as you may have already sensed from my voice, I'm not still convinced that um, I'm still not convinced that monthly charges should be dropped because somehow, I mean, intuitionally, I feel that's not really a good idea. But let's see if this is statistically insignificant. Right? If this is statistically insignificant, then is this really dropping this? call underscore 3. Let me see what is the value. Monthly charges is no longer there. Yeah, good. Now, if I remove the monthly charges, let me directly go ahead and build another model. So I'm going to call this xtrain sm. Again, I'm going to create a new frame of data, and then I'm going to say sm dot add constant, and I will take this value xtrain and use call 3 now, because call 3 is where I have dropped the monthly charges field. So now I'm going to create my third model. So logistic regression 3 or logistic model 3. Is that my third model? Why is it going to be my third model? 1 minute. How many models have we created? I think we have created only one. Logger 1. Then we did RFE. This was no, we created two models already. Yes, log M2 we have created. Correct. Yes. This is going to be my third. Correct. Yeah, I was doing correctly. Yeah. So log M3 will be what stats model.glm. Again, that same function here. I have to pass the y train and then x train sm, and I have to pass the family is equal to sm dot families. Sorry, dot. I think it was binomial. Yeah, binomial. This should be the name of the family. Now that I have got it, so what I'm going to do, I'm going to say res, or my model result is log m3 dot fit. So unless and until I fit the model, I will not be getting the summary. So I can now say res dot summary is this. Now if I do this, still see I'll no, I don't see any one other than this payment method mailed check, right? This was the one I believe we dropped earlier. So why don't we drop this also? Call 4 is equal to call dot drop, and we are going to use this one, access 1. Oh, okay, yes. I mean, this is not a data frame. Why should we accept it? So now I have column 4. Sorry, I have column 4, CUL4. This does not, this should not have the, it still has the monthly charges list. Why does it have the monthly charges list? I dropped it, right? Call 3. Okay. Sorry. Call 3. Sorry. Now it should work. Yeah. Yes. Okay. So I can now create again one more model. So I'm just going to make it faster and do a copy paste. So now I have to use call 4, and then I have to use this line to create my fourth model. I hope you are getting my point there, what I'm trying to do. So I'm just trying to figure out if these statistical measures, or the findings that I'm getting from RFE and VIF is helping me or not, because ultimately I've already scaled my data. My data is also not that much big, so it should idle condition work quite well. 0.05. There is still one feature here. You see, mail check is still there. Why? I dropped it, right? Call 4 I have used. So electronic check, yeah. Oh, sorry. I did a, yeah. Now this should be good, but this is still high. Multiple lines, yes. So why don't I take this and come back so that I don't have to. No, I can do one more. Why not call list 5 is call list 4 dot drop in the brackets this. Sorry, it should be call 4. So now what I have, I'm going to take again, I'm just making sure that I don't disturb the previous model. So if I append on the same model, right, that's a bad practice actually. We should never do that, because then what happens is we lose the history. So we can never get back and go to the history. We will never be able to compare things. That's the reason why I'm not doing it. So now I'm going to do res is equal to log m5 dot fit, and and then res dot summary, right? This is what we do. Now if I look at this again, I have one more. Streaming movies, yes. Streaming movies, yes, was not there earlier. Yes, it was there. Sorry, I missed it. I missed it. I should have taken this also. Let me save my time. Let me take this here. Let's see if this is going to call underscore 5. So yeah, this is call underscore 5. I believe streaming movies. Yes, no, it is not deleted from there. Uh, should it be like this? Let's see. I believe it might be like this. Invalid syntax. Yeah. Oh, okay. So to remove this. So streaming movies. Yes, that is gone. Yes, I believe that is gone now. Yeah. So let's fit the model and see how it is going. Now this looks quite good, right? Now this looks quite good. There is no value which is going to. But let's not get excited. I mean, we have just employed VIF, right? So let's just try to look at again. We are going to look at the predictions now. So I'm going to say Y train. No, I cannot directly go into prediction. Yeah, I think I can. So Y train pred, okay, is equal to X train SM. This is what I'm going to use over the model RES. So I'm going to use a function called res dot predict. So this should predict my values, but I have to reshape it. And the reason why I'm reshaping it is because I would like this data to be a 1D array. And that's the reason why I'm doing a reshape. Okay. So if I look at the values now, these are the values that I've got. So it has become a 1D array. In a single row, I've got all the outcomes, which is the let's say the expected predictions which I have for the training data. So I can even do something like this. So I can do, yeah. Okay, no, sorry. Why? This is a 1D array. It shouldn't be this one over here. So it should be this, right? So yes, I have only one row, so there is no point of giving anything before the colon. After the colon, I'm giving 10, which means it is printing with the values for a 10. Very good. Now that I have the prediction, okay, then what I'm going to do, I'm going to create y train prediction final again, and then here I'm going to give a churn probability similar to what we have done in the last the session. Also, I'm going to just take y train pred and put it over here. So I have y train pred final, which has a value which is something like this, right? So I had these values already, right? I had these values already. If you remember, y train pred final is a data frame that I had created earlier also in my earlier models. So I already had this earlier, and there was a column already called churn probability. I've just replaced it with my new y print pred, y trend pred, right? Now what I'm going to do, I'm going to calculate the predicted value. So how I'm going to do that? Y trend, sorry, just need to look at the y trend pred final. So y train predict final, and in the column name was what? Predicted, right? So I'm going to say predicted is equal to, I can use a lambda function here using a map function similar to what I've done earlier. So what do I do? Y train pred final, and the column name is churn prob. So I'm going to say churn prob, churn underscore prob it was, yes, churn underscore prob, uh, prob. And here what I'm going to do, I'm going to use a map function, and I'm going to say lambda x. Okay, give me x value should be 1 if x is greater than 0.5, else 0, right? So my logic, I believe you remember the logic that in the last class, in the last session also we have used. So I'm simply going through the churn probability column. If the value of churn prob column is more than 0.5, I would like to map the value 1 to the column predicted. Okay, now that I have got it, then let's see why train y train pred final dot head. So even now also I have two misclassified points over here. Let's check the metrics, right? This time I'm not using the manual calculations of the confusion matrix and so on. I'm directly going into sorry, why do I need to use print? I can directly go into metrics, right? That was a library metrics dot accuracy score, and inside the accuracy score function I have to give two values. What uh, that is uh, this dot churn, which is the actual value, and this dot predicted, which is the predicted value. So the value is around, again we have got a model which is only giving us 80% accuracy. If you see last model also I believe was close to 80 only. Let's just sorry, let's just quickly confirm. So where is the value? Yeah, I think this was the value, right? So it's quite close. It's really quite close. So I can even look at the confusion matrix. So let's see. The confusion matrix looks similar. Let's try to remember the number 3181583. Okay, 3181583. Let's see if it's good. Uh, Confusion matrix 3181583. Yeah, it's changed a bit. And it's not exactly the same, but it's, I mean, the accuracy is still the same. I mean, we are not gaining anything by doing that VIF thing that we have done, which brings us to a very very good point, irrespective of whether we consider the columns that we have just dropped, right? So monthly charges has no significant effect on the model. So even after scaling of the data, monthly charges, the field, the value of this field has no impact at all. Whether or not it is there in the model does not change anything. This will be difficult for you to explain in front of your clients, because at least it will be difficult for me, to be very honest, because if I go in front of a client and then I have to tell him or tell her that ma'am, you have this um, uh, this finding which says that if the customer is spending more money or less money, that does not really define whether the customer will charge or not. That's, I mean, from my perspective is a bit difficult to explain, because if you are charging more, there may well be a good probability that people will leave, right? If I'm going to have my products overpriced, then there can be a churning issue with the customers. That's what I feel. Okay, that's what I feel, but maybe this model does not feel that, right? I mean, as per my model, that's not really the case. Okay, so I think we have done this. We can again do another modeling by dropping the total charges and trying to find out what is going to be the accuracy, but I don't think that's really going to help. I have some gut feeling that it's not really going to help. Okay, it's really not going to help. So let's look at some other aspects of the uh, of the predictions. So one of the things that we we will need to understand is that there is always a concept. There is always a concept of uh, not only the accuracy should be considered as a metric, right? I mean, accuracy is a good metric. Here we got the accuracy, and it's quite good. I mean, if you're getting a model with 80% accuracy, that's really really good. Then is that the only measure uh, of the model being good or bad? Unfortunately, the answer is no, because we would need to also verify the uh, the way the the essence of the calculations that we are doing. So for example, if we have greater accuracy, right, from the confusion matrix definition itself. If I go back to the confusion matrix definition which I have, then I know that it means that I am correctly identifying the positives as the positives, right? I am correctly identifying the positives as the positives, and I am correctly identifying the negatives as the negatives to a very good extent. If let's say the accuracy of the model is high, so that's what it means, right? So if I have good accuracy of my model, simply put, I have my true positives and true negatives, which are really good, right? Uh, so why I am saying the true positive and the true negative being good is because if they are higher, then the denominator or the denominator really does not have any uh, effect there. So let me write the diagram, then it will be clear, I believe. So what I can do, I can maybe take a whiteboard. And I can take a whiteboard. Let me just see, or maybe I can draw over here only. So I can say, so what we did in case of the confusion matrix is that I've taken, let me change the color. So I've got a matrix which is something like this. This I'm calling the confusion matrix because I have four numbers here. So I have, let's say, the predicted values in the columns and I have the actual values in the row. So I have, let's say, positives. Okay, so positive for me in this context is not churned, right? If a customer has not churned, that is positive for me. But if it is a churned, that's a negative for me, right? So 1 and 0. Now this is, or it can be the ulta, right? It can be the opposite as well. So that is really not a problem. But what I am more interested in is the values which is going to come over here. So we have to design what is the positive value and the negative value in our case, and then what we need to do is to find out the values which come in these cells, and according to what we choose, in this case I have chosen not churned as the positive value, then the value, the number that comes over here in this cell is also known as true positives, because I've identified correctly all the people who have not churned as not churned, right? So that's called the true positive, and this value over here is known as the true negative, because these are actually the negatives and I've identified them as the negatives, right? But then what happens is, uh, this value is where they are predicted to be churned, but actually they did not churn. Actually they did not churn, right? So what can I say about that point? Okay, this is false positive. Okay, this is a false positive. This value over here is known as a false negative. Okay, this value over here is a false negative. So a total of all these points which you have gives you the total number of rows which you have in the data, right? So total number of rows is equal to summation of all these values, right? That goes into the denominator. So that goes into the denominator when I'm calculating the accuracy. If you remember, when we calculated the accuracy manually, we took the entire sum. We have taken the entire sum and we have put it into the denominator, right? Now on the numerator, we are going to have true positive and true negatives. So the sum of true positives and true negatives is where I have correctly identified the cases. So number where I have correctly identified the cases divided by the total number of observations is my accuracy of my model. Now the problem here is, just because I have a very high uh, true positive plus true negative rate does not always mean that it's a good thing. Why? Because let's try to define two terms and then we'll come to know why this is a problem. So uh, the first point I would like to define, is going to be called, let's say, the precision. Okay, I'm going to call it the precision. Okay, so precision is basically, or maybe what I can do, I'll clear the drawings. Let me take a text box. It'll be easier for me to explain with a text box. So let me take a text box, because somehow today my mouse is not working very good. So true positive, true negatives, I have already taken. So let's see what is the definition of precision. Sorry, what am I typing? Guess some issue with my Zoom. Oh, okay. I see Sarang's got dropped off, so I've just added him back. Give me 1 minute. Let's see if he was able to join. Hi Sarang, so very able to join now?
Yeah, yeah. I
Yeah.
think I missed the last 5 minutes. Don't know why.
Okay. Yeah, no
Mm.
problem. We have just started looking into the fact that why, let's say, accuracy is not really a good measure, right? So that's what we are
Yep,
trying to find
yep,
out.
got
Okay. Let me just clear all the drawings and clear this. And hope you can see my screen, right?
it. Yes, yes, I can.
Yeah. So, okay. So what I'm going to do, I will take true positive. If I take the true positives, okay, if I take all the cases where I have identified things properly, so that's known as the true positive, and divide that, okay, divide that by the true positives and the cases where I have false negatives, okay, false negatives I have. So false negatives is what if I look at the confusion matrix and I have outcome 1 as this, 0 as this, which is the predicted outcome. So these are the predictions, and my actual outcomes of 1 and 0 are represented like this. And this becomes my true positive, and this becomes my false negative. Right? This becomes my false negative, and this becomes my false positive. Okay. No, I think false positive will be this. I'm sorry. False positive will be this. False negative will be this. Okay. And then true negative is this. Okay. So true negative is this. True positive, false negative is this. So now if I look at the proportion of true positives as compared to true positive plus false negative, this gives us what is the weightage. So what is the weightage of this prediction against class 1 that I have done, or the true classes that I have done. Now this terminology over here, okay, this terminology over here has two meanings. It is either known as sensitivity, okay, or it is either known as sensitivity. In some texts it is known as sensitivity. It is also known as precision. Okay. Why it is the precision is because it is the approximate value of how much correctly you have been able to group the positive use cases. So now I'm only going to concentrate for some time on the positive cases. If I do that, how much will I have done with the one cases or the plus cases or the positive cases? That's what the uh, uh, the formula which we see on the screen is going to give us. Otherwise known as the sensitivity, or also known as the precision of the model. Now, if I look at the other side of things, right? So the other side of things is just a moment. Let me recall what I just said. Uh, Correctly classified points. Yes, true. Yes, this is correct. Yes, no mistakes there. So now the other point is that true negatives. If I have the true negatives, these are also correctly identified, right? So true negatives here in this tables are also correctly identified because I predicted 0. Actually, it was 0, right? So no problem. But if I divide true negatives by this entire column, or this, if I divide true negatives, if and better, by FP. Okay, so this is FP and this is FN. So false positives plus true negatives. If I divide true negatives by the sum of this entire column, then I get the weightage that I get against the zeroth value, or I get the weightage against the negative classes. Now this weightage that I am getting is known as this terminology that I'm getting is otherwise known as specificity. Okay, this terminology is known as specificity, or it is also known as recall. Okay, it is also known as recall. Now, a combination of precision and recall, or a combination of sensitivity and specificity is what really determines how good or how bad my model is, right? Because this ratio is really very important. It's like, if let's say, if let's say I have 200 people in my housing society, and unfortunately there are at least 2 to 3 people, okay, let's say I'm also one of them, unfortunately, who are suspected to have this COVID-19 virus. So now that I may have met 10 more people, 20 more people, you don't know that I have a lot of friends. So I may have gone and met a lot of people. So why to take a risk? The municipality or the officers from the municipality visit our society the moment they come to know that I have been tested positive. So they try to test everybody in the society. So they take a test of all the 200 people, right? If they take a test of all the 200 people, and there are even 5 people who are predicted incorrectly, then you try and see what is the impact here. Now I have 5 people. Okay, I have 5 people who are predicted incorrectly. Out of how many? Out of 200 people, right? I have 200 people, out of which 5 are predicted incorrectly, which means my accuracy is what? If I go by the definition of accuracy, I'll sum up true positives and true negatives, the cases that I have identified correctly, right? So if I have incorrectly identified 5 people, how many have I correctly identified? 195, right? 195 I have tested correctly, and the predictions are also correct. So which means 195 divided by 200 is my accuracy. But look at the rest 5 people, right? The 5 people whom I have identified incorrectly is now going to be a problem, because only because of those 5 people, it may well be a fact that within the next 2 weeks, now I had only 5 people or 10 people or 15 people who were affected. Now that I have incorrectly classified 5 people, those 5 people might be responsible to spread the disease now to 50 more people, even outside the society, because they'll roam around freely, right? They'll roam around freely considering they don't have the virus, and then they'll meet people. Maybe they will forget to put on their mask, and that will be a disaster, right? So that's the reason why, if I only look at this accuracy score, that's not really a good measure. It's not really a practical measure. It's a mathematical measure. Correct. Yes, true. We have a mathematical measure. Right. Uh, Clearly, that's a good thing to do. Right. But then it's not really good always. Right. What are the ways now? What are the ways in which I can correct this? Okay. So what are the ways that I can really correct this? That there are two ways actually. One of the ways depends on a mean, a concept of a mean, which is known as harmonic mean. Okay, it depends on a concept of harmonic mean. Now, harmonic mean of any numbers, okay, let's say x and y, is given as 2 multiplied by xy, or 2 times x multiplied by y divided by x plus y. The harmonic mean is not really something which is naturally available in the nature. So we don't see much of an example of harmonic mean. But using harmonic mean, or using the principle of harmonic mean, using the principles of the harmonic mean, we can get a score, we can get a metric which is otherwise known as F1 score. So the first metric that we can use to say whether or not we are really doing a good job, right? If at all we are doing a good job, is known as the F1 score. Now, what is this F1 score? F1 score is going to be kind of inspired um, from the concept of the harmonic mean. And what we are going to say is that I'm just going to take or calculate F1 score as 2 times. Okay, I'm going to take 2 times of precision. I'm going to write precision as P, recall as R. Okay, so 2 times P multiplied by R. Okay, 2 times precision multiplied by R divided by P plus R. Right. So if I take this score, this gives me a good idea. Okay, overall, this gives me a good idea of how good or how bad the model really is, taking care of the practical considerations that I have just told you. That was just one of the examples that I've said. Right now, uh, if one score um, is actually having a few flaws, the flaws is that there's always a possibility that if you have not treated your outliers in the correct way, or if you have uh, some uneven variety of data within your data set which somehow you are not able to take care of, then what happens is this score gets elevated, because your denominator in this case, being a plus, being an addition, is entirely dependent on how you have treated the data. Right? If you have treated the data properly, like we have scaled it, we have one hot encoded it and so on, so that becomes mandatory. If we have done that, in our case we are lucky we have done that, then this F1 score might be of good help. But then we can't always be sure on this, because mathematically it has been seen that in various use cases also we have seen that compared to F1 score, there is yet another calculation, the one that we are going to look at now. uh, that calculation actually gives uh, a better representation of the accuracy. Okay, and that calculation is nothing more than a curve. It is basically a diagram. It is basically a chart which we are going to draw. Okay, and then after we draw that curve, or after we draw that chart, we come to know uh, how much is the area. Okay, how much is the area which is covered by that graph, which ultimately will tell us what is going to be our benchmark, or what is going to be our um, uh, uh, the value which we can consider as the cutoff. Right, so the value which we consider as the cutoff will now be defined by the findings from the ROC curve. So that method is known as ROC curve. Now, what I mean by ROC curve is, uh, in the full form of ROC is, I'm just going to write it over here. It's called receiver operating curves. So basically, as I said, it's a curve. Okay, it's a chart, and the chart, more often than not, it's not going to be exactly like this. It may not be exactly like this, but it's going to represent a form. Okay, it's going to represent a form which is, let me just change the color, which is something like this. Yeah, it's going to look something like this. Right, from here we are able to calculate, what is going to be the cutoff point. Okay, the cutoff point where we are getting good amount of uh, accuracy. Okay, how we get that is that, let's say, oh, this is the curve that we have got. Now what I'm going to do, simply put, I'm going to define the variables first. That we have got a curve, or we are drawing a curve, we need to know what is x and y. So y in this case, okay, y in this case is otherwise known as my true positive rate. Okay, we have already seen what is a true positive rate. Okay, true positive rate is what we are trying to figure out, how much uh, uh, true values have we really identified. Right, how much true values we have really identified. So that is nothing but the sensitivity, or the precision. Right, so that's what is the true positive rate. Okay, that's another name. Okay, that's another name by which we can call it. So I'll plot on the y-axis the true positive rate, and on the x-axis I'm going to plot the false positive rate. I'm going to plot the false positive rate, or my recall. Okay, or I'm going to plot my specificity. So there are three names. It can be called specificity, it can be called recall, or it can be called the false positive rate. On the y-axis I'm going to plot the true positive rate, or the precision, right, or the sensitivity. Right, now what am I going to plot that I'm going to get a value like this? How am I going to get a chart like this? Because I just have one value for a TPR. Right, I just have one value for this and one value for this. How can I get a curve? I can get a curve by means of doing an iterative process. Okay, by doing an iterative process of selecting multiple numbers or multiple various different numbers as my threshold, right? So what I am trying to do is I'm trying to, let's say in my lambda function, right, I've selected 0.5. So why not I try with 0.1, then I'm going to try with 0.2, then I'm going to try with 0.3, and so on and so forth, because I'm going to try with a different number here. Since I'm taking a very ordered set, which is like the 0.1 places different or away from each other, so clearly you can see that in this list I'll have 10 values, right? So I'm going to have, no, I'm not going to have 10 values, sorry, I'm going to have 9 values. I cannot have 1 as the threshold, right? So 0.1 until 0.9, right? So I'm going to have 9 values in this list. So I can take these 9 values and create 9 models. I can create 9 models by taking these 9 different values in this list, and then I'm going to compare. I'm going to compare the values of true positive rate with the false positive rate. Now I'm going to get a curve like this. Let's say I'm going to get a curve which will be like this, because after a certain point in time, it is not going to matter how much is the threshold, right? So the accuracy or the true positive rate is actually going to get stagnated after a certain point in time, right? Now what I'm trying to do, or what I am supposed to do, is that I'm going to draw a line from the origin of this graph. Okay, I'm going to draw a line from the origin of this graph until the time this curve, this ROC curve, has saturated. So until that stage, after which the ROC curve does not increase, right? So if that is the case, my objective now is to find out let me just take a bigger pen. My objective now is to find out what is the area. So what is the area which is covered under this curve until this line, right? So if this area is good, okay, if this area covered is good, and I am able to find out that specific point, let's say my point is 0.3, although that's a very bad choice, but let's say 0.3 is the threshold value where I am getting both good TPR and good FPR. That's my prima facie requirement. I should have good values for a TPR and FPR, because if I don't have that, then that's going to be a problem, right? That's going to be a problem. I think I have done a mistake. I just realized I have done a mistake. Let me just correct that. Okay, then and there, let me just correct that. Control Z I will do. Yeah, I just made a mistake by calling this an FPR. This false positive rate is not a recall. Okay, this false positive rate is not a recall and specificity. False positive rate is actually 1 minus true negative rate. Okay, 1 minus true negative rate is false positive rate, and true negative rate is actually known as the recall or the specificity. Sorry for the confusion, friends, I just missed out that part. So the x-axis is false positive rate, that's equal to 1 minus true negative rate, and one this true negative rate in this equation is the recall or the specificity, right? So when I'm doing this comparison, my idea is to find out the area under this curve, and basis the area under this curve, this is a concept taken from calculus world, where I'm trying to figure out that optimal value. Okay, that optimal value of my threshold, let's say 0.3, or let's say my optimal value is going to be 0.8, where both these values are really quite good. So I have good values for true positive and true negative rates. Okay, so if I have good values obtained for precision and recall, okay, then I can say that I am able to most of the times correctly classify the positive and the negative points, and hence I say I have a good model. Now the higher the number is, better I have, right? So what I mean by that is, let's say if I go back to the confusion matrix, this is my two values, I'm going to represent them as x. These are my two values which I'm mostly interested at, and they should be as big as possible, right? I mean, they should be as big as I can. So let's say I have again that 200 people example. Ideal condition, these two should add up to be 200, right? But I'm not going to get that. Maybe these two add up to be 195, right? If that is the case, then these dots over here, the one dot over here and one dot over here, representing the misclassifications, will only constitute of 5 values, which is okay, right? But then that's not really going to be decided by the accuracy itself. Now we are beyond the score of accuracy. Now we are not going to be considering the accuracy score, right? Our use case has now changed. Now I am only not going to only concentrate on people who are misclassified as the non COVID-19 patients. Now I'm also going to consider people who are identified as COVID-19 patients, but they did not had the disease. So both such kind of problems are now going to be taken care of, and I am going to have a much more robust way. Okay, much more robust way to validate my model. Okay, so this is how I'm going to validate my model. This is how I'm going to validate my model. This is how I'm going to find out which model is really very good, right? How am I going to calculate that? Let's take a quick pause. Let's take a quick pause here. Let's see if you are able to understand. Is there any doubt here until this point in time? Any doubts? I hope you're able to hear me, right?
Yes, Bombay, no doubts.
Okay. Okay. Right. So before I start drawing it, just a quick recap of what we just said with these all of these diagrams, right? So we are going to implement it. We will start implementing it now, or maybe we can do it in the next session also, because we are already almost out of time. So we can make a logical stop over here. But maybe before we do, let's just quickly review what we have just seen in the diagram. So essentially, what I'm saying is, to validate whether my model is good or not, I have two ways other than the confusion matrix, which is leading to the accuracy of my model. So not only by looking at the accuracy of my model, I'm also going to look at things like sensitivity and specificity, right? And how they are going to help me is by means of a tool that I'm going to use, or a technique that I'm going to use. Its name is ROC curve. ROC curve is going to demonstrate me overall, if I'm going to summarize, it's going to give me overall three things. First of all, it gives me a trade-off between sensitivity and specificity, right? That's what I'm trying to plot. Okay, that's what I'm trying to plot over there. Now, the closer the curve follows the left hand border and then the top border, the more accurate is the test, which means the closer the curve, okay, the closer the curve looks something like this, right? It is actually a better test. This is actually a better finding than a model which is this. Why? Because if I take a diagonal line, if I take a diagonal line which is something like this, okay, and now I will take a different pen. So the area, okay, the area which is covered by this line, let's say this is line 1, this is line 2. So the area, okay, the area which is covered by line 1 is actually less than the area which is covered by line 2. Okay, that's why it is called ROC. That's why it is known as the area which is under the curve. Okay, so the measure that we are trying to find out here is also known as, or the factor is actually defining whether L1 is better or L2 is better, is otherwise known as AUC also. So we are essentially trying to find out the area under the curve of an ROC plot, right? We are trying to find out the ROC curve, and we would like to maximize the area under the curve, right? The more it is actually maximum, then it is really very good. The more it is closer to this line, this orange line, let's say this orange line is L3. The closer my comparison of true positive rate and false positive rate is towards that orange line, the bad my model is, and the more outwards it is. So the closer the curve follows the left hand border and then the top border of the ROC space, the more accurate the test. So L2 is actually much good, right? And the more it goes towards a 45-degree angle, because this line is through the origin of x and y, so the angle over here is 45-degree, right? So the more my line, the more my comparison is closer to 45-degree, that's bad, really bad. Okay, now what I'm going to do to find these out, actually, rather I'm going to take multiple values. So I'm going to create an experiment which is going to use a methodology. Later on, we are going to look at that methodology in great depth. That's called bootstrapping. Okay. So what I'm going to do over here is that I'm going to bootstrap my way in which I'm going to take the samples, in the sense that I'll have a list of, in the next session, right? I'll have a list of the values of thresholds. Okay, the values of thresholds, as I just took an example of some time back. So I'll take a range of thresholds between 0.1 to 0.9 maybe. And then what I'm going to do, this curve, I'm going to plot for each true positive and in each false uh, positive cases for each and every of my actual points and the probability point. So rather than taking the whole count, I'm actually going to plot. I'm actually going to take into consideration each and every point, right? And then let's see how this curve comes up. And we are also going to find out the threshold value, the value for which the values of sensitivity and specificity is very good or in the acceptable limits. Once we have found out the values, then comes the business knowledge. If I have good business knowledge, I understand what is the implication of the true positive rate and false positive rate, I should be able to find out, or I should be able to determine what's going to be a good threshold. And then I go ahead. I simply build the model. I've already scaled my data. I've already gotten rid of all the variables that I thought I should be getting rid of. So I'm already done with my data preparation, right? So I don't need to do anything in that area. So I can simply create my model, and while creating that model, I'm going to select that threshold value, right? The moment I do, my model is ready, right? That's the best I could do with this data. That's what I'm going to conclude. I hope that was understandable, friends. So let me stop the sharing. If there are any questions, or else we can close the session as of now, and we will continue from tomorrow. Is that fine?
Yes, Bob, maybe I have a question which I can raise
Yes.
tomorrow.
Okay.
Okay?
Okay. Or
Okay.
maybe you can post it on the group also.
Sure, sure, sure.
Okay.
Okay.
Okay then. Thanks, Anang. Thank you, Rohi.
Thanks,
See you
Bob. Good
tomorrow.
night.
Thanks, Mohammed.
Good night.